Welcome to the 10 o'clock presentation, Hardware Virtualization Rootkits by Dai Zovi.
Excuse me. All right, well, good morning. I'm a little slow because I haven't had my coffee yet this morning, so I will try not to put myself or any of you to sleep. What I'm talking about today are hardware virtualization-based rootkits. Basically what these are, there's no real good name for these, are rootkits that take advantage of virtualization features in modern processors like the Intel Core series and AMD 64 chips to implement rootkits and basically run a rootkit outside of the operating system. You'll notice the nice little keynote transitions. It's not just visual fluff. It's a metaphor for how the virtualization technology and Intel processors work, which I'll get to later. So this is what I'm going to talk about. I'm going to give an introduction to my company and myself, and move on to overview of how virtualization works, hardware and software right now, and introduce basically the background on the Intel virtual machine extensions and basically what they can do, what their capabilities are, and how they work, just to sort of give you an idea of just how easy it is to make a rootkit out of this. And basically then I'll talk about my rootkit that I call Vitriol. It's a VTX rootkit for Mac OS X, and I will do the all-important demo to prove that I'm not completely lying. Who are we? We're Matasano. We're a small company. We do services, and we're working on a product. We are Dave Goldsmith sitting right there, Jeremy Rausch, Thomas Tacek, Window Snyder, and myself. We've done a number of presentations over this conference, so you've probably seen some of my cohorts also presenting. What we do, we have several services. Deploy Safe, basically this is for companies who are looking to deploy third-party software. We'll come in, we'll bang on it, make sure that basically you're not putting your organization at risk by deploying the software. For software vendors, we do Ship Safe, which is really tough to say, but I should have practiced. And this is basically where we audit your product before it actually ships. And we're coming out with our first product around the end of the month. It's not so much July. We're hoping to get it out before the end of August, so we're not completely lying on these slides. That's called Clockwork. And the big question is, why am I here? I'm talking about hardware virtual machines. And basically, virtualization is really hot right now. We're getting hardware support for it. A lot of organizations want to drop costs and basically still maintain logical separation between hosts. And the answer to this is virtual machines. And so, VMware is basically everywhere. Basically you save power, save trees, everyone's happy. The only concern is that basically a lot of these features, once they move into the hardware, can be taken advantage of by malware. And right now, we don't really have much to prevent that or stop that. And so I really want to basically bring these issues to light, especially before further extensions based on virtualization, like sort of the next generation computing-based Palladium-style stuff, where basically having hypervisors that are actually and VMs that actually protect, are resilient against the host, and that's the design goal. Before those become available, and basically rootkits can also take advantage of that to make sure that there's absolutely no way that the host can detect their presence or modify them. So right now, there are ways to detect hardware VM rootkits, detect the R in a hypervisor system. So it's something good to get thinking about at the moment. And basically what I'm going to show is kind of the cool trick of, so a hardware virtual machine rootkit can install itself, and basically by migrating a running operating system into a hardware VM, and then just install itself as a hypervisor around it. And basically once it's there, it controls every aspect of the operating system, and it can hide itself in memory, basically unmap its pages from the guest, now guest OS. It can mediate access to memory, and basically, be really difficult to detect with our current, techniques, and at the same time have the same level of access that a normal rootkit would give. All right, so give a little background on basically how virtualization works. Basically, if you think about it, look back maybe, 20 years to basically, modern operating system design. The whole idea was the operating system kernel was a virtual layer between the apps and the hardware. And basically with multiprocessing, time slicing between processes, basically every process was under the assumption that it had its own dedicated processor. And basically device access was abstracted through system calls. And this was a radical innovation back when mainframes had to sort of swap the operating system out to run an application and then swap it back in. Big pain in the butt. And so basically, what we're doing, the virtualization that's happening now is just another layer of abstraction in this sort of same vein. And basically, my presentation skills, you have to excuse, are pretty primitive, but I'm actually taking the evolutionary leap to have diagrams in them. So notice this is the first diagram. It's 3 colors. It's not just black and white diagrams. It's actually in color. We have the hardware in gray because it's a gray box, kind of nice little metaphor there. And basically have applications that are multitasked on top of the operating system, which is the sole basically entity residing over the hardware. Now, fast forward 20 years, and we're looking at software-based virtualization. Basically, this is stuff like VMware, Virtual PC, Box, a lot of the open source projects as well. And what this allows you to do is run multiple operating systems concurrently, which is awesome fun because you can play with random operating systems that would never support your hardware. And how this works is there's a new layer introduced that is called the Software Virtual Machine Monitor. And what this is this basically runs between the operating system and the VMs, and it abstracts hardware so that the VMs can, so that the access to the real devices can be multiplexed, can be virtualized. Instead of having the VMs hit the disk directly, you can basically simulate a disk, and have everything written to a file. And also what, added benefit of it is that, the VMM emulates well-behaved, nice hardware. I think everyone at some point has bought the $16 sound card from, CompUSA that, is totally crap and the driver never works. And so basically, trying to run legacy operating systems or anything else, the hardware presented by the VMM is, nice hardware. It's like the Sound Blaster 16 that, the interface to it has remained the same since, 1990 or whenever the first Sound Blaster came out. And basically, the way that the way that software has typically done this is either instruction interpretation or translation. And so basically, we have things like PowerPC. We have PowerPC for Virtual PC running on PowerPC. And what it does is they will the earliest versions like PowerPC does this. They interpret processor instructions individually, and it's basically just one big emulator. And it's kind of lightweight virtualization. It's slow. It basically emulates all the hardware directly. And when you're running on a if you're running on on a RISC system and you're emulating like x86, it's usually pretty easy because you have spare registers, so you can do a pretty much a one-to-one instruction mapping, and it can be pretty fast. The other way around usually gets slower. So basically, the next approach is to actually do what's called binary translation. And what binary translation does is it basically breaks the entire execution stream into basic blocks. A basic block is basically a sequence of instructions that have no jumps or transfers of control in them. And so what it does is it basically divides these, builds a control flow graph basically out of these basic blocks and translates them individually and caches basically the most used ones. And this is sort of a memory time trade-off where obviously you can't translate the entire operating system in every application they run, because when you're virtualizing an operating system, they're running one application after another. You can't translate the content of everything they have on disk. So what you find is that basically like a single program, 90% of the time of execution is spent in 10% of the code. And basically by doing the approach of binary translation where just break it into the blocks, translate it, cache them, and you basically have a sort of a hash table of destination address to that basic block. You keep those in memory. You can sort of dynamically size how big your cache is, and you get decent performance. If anyone has used Virtual PC on a Mac, they know it's usable, but it's just really, really painful. And it's usable enough that they actually, people bought it, people use it every day. but it's really not that great. So when you're on the same architecture, you can take the third approach, where basically all you have to do is translate privilege instructions. This is closer to what things like VMware do, where basically you're on the same architecture, so you can just run user code natively. You can run it straight, no translation necessary. But you have to make sure that when you're running the kernel code for the guest OS, it doesn't actually tamper with the host operating system or the virtual machine data structures, anything like that. And so what they usually do is basically they'll scan the instruction stream for privilege instructions and translate that. And I think I have a slide right here, a little more detail on how VMware does it with yet another diagram. Basically, the idea is the virtual machine monitor. This is sort of the bridge between the guest operating system and the host operating system. And it runs usually in ring 0. It's a kernel module in the host OS, and it keeps itself in the address space of the guest OSs as well. And basically, what the approach VMware takes is it'll translate all the guest kernel code, because that's it has to make sure all the privilege instructions are emulated correctly. They don't tamper with anything, and basically disrupt the operation of the VMM or the guest or the host OS, because breaking out of a VM, getting to the host is basically game over for a lot of the scenarios that people use virtual machine technology for. The guest user code doesn't have to be translated. It can be run directly. It's no problem. And basically on a context switch between the host and the guest, all the host memory is unmapped, so the guest has absolutely no access to any memory that it shouldn't. And basically other tricks are used to protect the virtual machine monitor memory and data structures from the guest OS, so it can't tamper with them while it's running, and try and use that to bust into the host. So now we get to past the review stuff, get into new stuff, and this is the approach taken by hardware virtualization. And basically how this works is you have on top of your hardware you have the VMM, which actually runs parallel to a low-level HAL. People have different names for it. And then the virtual machines are run directly on that. Notice there is no host OS in this. Basically, the VMM acts as the host OS. There's really you can use treat one of the VMs as kind of the authoritative one, and it'll provide a lot of services to the VMM. Or basically, the VMM can be a very lightweight operating system that just provides device access and basically just has a device emulation layer that the VMs use, and it just basically multitasks between them. And so how a lot of these work basically is the processors. Intel processors have the 4 rings. RISC processors have basically just supervisor mode and normal mode. But we'll talk mostly about the Intel ones, because the Intel architecture, because that's what everyone's doing right now. Basically, what the virtualization does is, just as it basically abstracts all the state of the processor beyond ring 0. So there's a special set of instructions that can only be executed in what they call a root domain, and basically that's how they have a fully privileged ring 0 and a lesser privileged ring 0. And what it does is basically we'll use a memory page to